What are the main equations used in orbital mechanics? Have you ever wondered how spacecraft navigate through the vastness of space? The answer lies in the fascinating world of orbital mechanics, which relies on several key equations. These equations help us understand the motion of objects under the influence of gravity. Let's break down the main equations that play a vital role in this field. First up is Newton's law of universal gravitation and motion. This law states that the gravitational force between two masses is determined by their masses and the distance between them. The formula is straightforward. The force equals the gravitational constant multiplied by the product of the two masses divided by the square of the distance between them. This law, combined with Newton's second law, which relates force to mass and acceleration, governs how objects move in orbit. Next, we have the Vis-viva equation. This equation connects the speed of an object in orbit to its distance from the central body and the semi-major axis of its orbit. The equation shows how velocity changes depending on the position of the object along its path. It applies to various types of orbits, including elliptical and hyperbolic. Another important equation is the equation of the orbit, which describes the shape of an orbit using polar coordinates. This equation expresses the distance from the central body in relation to the semi-latus rectum and the eccentricity of the orbit. The eccentricity tells us whether the orbit is circular, elliptical, parabolic, or hyperbolic. Then we have Kepler's third law, which gives us the orbital period. This law states that the time it takes for an object to complete one orbit depends only on the semi-major axis of its orbit and the gravitational parameter. This means that the size of the orbit is what matters, not its shape. Specific orbital energy is another key concept. This equation calculates the total energy per unit mass of an object in orbit. It helps determine whether an orbit is bound, unbound, or escape. A negative value indicates a bound orbit, while a positive value suggests an escape trajectory. Lastly, we have the angular momentum per unit mass equation. This equation helps us understand how the shape of an orbit is related to the velocity of the object. It is essential for calculating the semi-latus rectum, which is important for determining the orbit's characteristics. These equations form the foundation for calculating spacecraft trajectories and satellite orbits. They allow engineers to plan missions, maneuver spacecraft, and predict positions and velocities throughout a mission. Understanding these equations is essential for anyone involved in space technology, whether it's launching satellites or sending probes to distant planets.